If the objects in a system are moving, then the center of mass of the system may also be moving. What is the relationship between the velocity of the system center of mass and the total momentum of the system? Okay, so conservation of momentum, as it relates to the system center of mass, we're going to take our net momentum, so add up all of the objects' momentum of the system. Net momentum equals our total mass times the velocity of the center of mass. That is your relationship. Remember, relationship means equation. During a collision, how does the system center of mass change its motion? Well, the center of mass doesn't change its motion. So there. In a collision. Momentum is conserved and mass is conserved. Momentum and mass are conserved. Momentum and mass are conserved. Balancing carts demonstration. Remember the two carts that pushed off of each other balanced. What was the speed of the center of mass before the cart sprung? What was the speed of the center of mass after the cart sprung? Explain why. The center of mass before they sprung, well, the two carts are just at rest and there's a spring between them. So the initial velocity of the center of mass is 0. Nothing was moving. After the velocity of the center of mass, well, if momentum is conserved, you've got one going left and one going right. Velocity of the center of mass, in the end, would then have to equal 0. So the carts are moving, but the center of mass for the entire system is staying put. It's staying right where it started. In order to change the motion of the center of mass, the system must have an unbalanced external force, because the way you change the motion of anything, whether it's a system or an individual object, is to have an unbalanced force acting on it. That's Newton's second law. Have an unbalanced force. What is the relationship between the acceleration of the system center of mass and the forces acting on it? Again, we're going to look at the net force and total mass. So the relationship between those two is the net force on the system. So only things acting on the system, not the internal forces. So the external net force equals the total mass times the acceleration of the center of mass. A ball in space is made up of 8 pieces. Initially, the ball passes point A with a constant speed. When the ball passes B, the ball explodes into 8 pieces. There's a wall located at C. When does the center of mass change its motion? Okay, so I'm going to create a motion diagram for the center of mass. It's going to look like this. So at A, it's going to be here. Then it's here. So the center of mass is moving. And then what happens at point B? Oh yes, an explosion. Pieces go flying in this direction, in this direction, in this direction. It's only 8 pieces. So these are just dots. So remember, momentum is still conserved at B through the explosion. So you have pieces going up and to the right. So you have pieces going down and to the left, up and to the left, down and to the right. All of those momentums canceling each other out, and the momentum of the center of mass is continuing on its merry little way. And then eventually the system's center of mass, well, it's not going to hit C, is it? Here's what's going to happen. These pieces that are sent off to the right are first going to hit C. And then what happens? Then those pieces are going to crash and fall down. As they crash and fall down, what's happening at point C? We have a force acting on them that is not part of this ball system. So this is an external force. What type of force is it? This is a surface, so it's a normal force. So what's the question? When does the center of mass change its motion? When there's an unbalanced external force acting, in which case it's not when the center of mass reaches point C. It's not when the ball explodes. It's when the first piece hits the wall and has a external force acting on it. Hits the wall and has an external normal force acting on it. That first piece falls down, then the next piece hits the wall, and then all of a sudden there's this change in motion that is not natural. If it was an explosion, that's fine, because the system center of mass would just continue because there's no net force acting. Even though you might say, but there must be some net force to make that thing explode in the first place. Not if it's an internal force. If it's just like a ticking time bomb and it just is traveling and then whoosh, blows up, that's very different than applying a force from outside of the system, which is what we're doing with the wall.